The 24-wheeled steam monster, that was so powerful it tore its own freight trains apart. There is a version of too much power that looks like failure. Not because the machine broke down, not because the engineering was wrong, but because the machine worked exactly as designed. And that turned out to be the problem. In 1914, the Erie Railroad took delivery of something that had never existed before. A locomotive so large, so heavy, so theoretically capable of pulling that engineers had run out of conventional ways to describe it. It had 3 full sets of driving wheels, each powered by its own steam engine. 24 driving wheels in total. A boiler the length of a house, a tractive effort, the raw pulling force at the rail, that made every other locomotive on the network look like a toy. It was called the Triplex, and within a few years of entering service, the Erie quietly stopped using it. Not because it could not pull, because it could pull too hard. Hard enough to snap the steel couplings connecting its own train together. Hard enough to tear freight cars apart at the joints before they ever moved. This is the story of a machine that was defeated not by its weaknesses, but by its strengths. To understand why someone built a locomotive this extreme, you have to feel the weight of what American railroads were hauling in the early 20th century. Coal, ore, steel, timber. The raw material of a nation building itself at speed. All of it moved by rail, in trains that were getting heavier with every passing decade. The problem was the mountains, specifically the Allegheny Mountains, which the Erie Railroad crossed on its route between the Midwest and the Atlantic coast. Grades steep enough that a locomotive capable of cruising flatland at speed would stall completely on the climb. The industry's solution was helpers, extra locomotives attached to the rear of a train to push it over the summit. Expensive, slow, operationally complicated. What if you built a single locomotive powerful enough that it did not need help? That was the question, and a man named Johnny Meyer had an answer. Meyer was an engineer at the Baldwin Locomotive Works, the most prolific locomotive manufacturer in American history. He had been watching the helper problem for years and arrived at a solution that was either brilliant or deranged, depending on how generously you read it. The conventional steam locomotive of the era had 1 set of driving wheels. Some of the largest had 2, using an articulated design that allowed the chassis to flex around curves. Meyer proposed 3 complete sets of driving wheels, 3 separate steam-powered engine assemblies, all connected to a single boiler, all turning simultaneously, all pressing against the rail at once. The numbers were staggering. The Erie Triplex, formally classified as a 28882, which describes the wheel arrangement from front to rear, stretched over 100 feet long. It weighed more than 850,000 pounds in working order. That is roughly the weight of 60 average family cars sitting on a single set of rails. And the tractive effort, the raw pull at the wheel, when they finally tested it, the moment they finally put that number on paper, it stunned everyone watching. 160,000 pounds of tractive effort. To put that in human terms, standard freight locomotives of the era were pulling somewhere between 60,000 and 80,000 pounds. The Triplex more than doubled that. On paper, it was not just a better locomotive. It was a different category of machine entirely. The Erie ordered 3 of them. They were named after senior railroad executives. They were photographed from every angle. And then they went to work on the Allegheny grades. That is where everything started to unravel. The first thing you need to understand about a freight train is that it is not one object. It is dozens of objects, individual cars, each connected to the next by a coupling. A steel link, precisely engineered, rated to absorb specific levels of force before it fails. Those ratings had been calculated for the locomotives that existed, for the forces that a conventional engine could realistically apply. Nobody had calculated them for the Triplex. When the Erie cruised back to Triplex up to a loaded coal train and opened the throttle, the force that transferred through the drawbar was unlike anything the equipment had been designed to handle. Not larger by a small margin, larger by a category. The couplings held, briefly, then they did not. Steel rated to survive a normal locomotive's pull simply gave way. Cars separated, loads shifted. In some cases, the locomotive pulled so hard against a stationary train that it damaged the cars themselves before a wheel had turned. It was a problem so fundamental, it exposed something the designers had not fully reckoned with. Raw power, at a certain scale, stops being an asset and becomes its own constraint. The triplex could generate more pull than the infrastructure around it could absorb, and that meant the infrastructure was the ceiling, not the machine. But the coupling failures were not even the deepest flaw. They were the most visible one. The deeper problem was steam. A steam locomotive generates power by burning coal to heat water into steam, which then drives pistons and turns the wheels. The balance between generation and consumption is everything. Use steam faster than the boiler can produce it, and pressure drops. Power drops. The locomotive weakens under load exactly when it needs to be strongest. 3 engine sets drawing from one boiler created a demand the boiler could not sustainably meet. At low speeds, the speeds the triplex was designed to operate on mountain grades, all 3 engine sets were working hardest simultaneously. Steam pressure would build while stationary. The moment the locomotive began climbing under full load, pressure began to fall. Crew reports from the Allegheny runs described the same experience repeatedly. The triplex would start well. It would grip the rail and begin to move the train. Then, somewhere on the grade, the power would quietly begin to desert it. Not suddenly, gradually. The way a fire dims when the fuel runs low. By the time it reached the summit, if it reached the summit, the locomotive that had pulled away with 160,000 pounds of tractive effort was delivering considerably less. Sometimes not enough to have been worth the attempt at all. The machine that was supposed to make helpers unnecessary sometimes needed helpers itself. The Erie kept the triplex locomotives in service for a surprisingly long time, considering how quickly their limitations became apparent. The railroad had invested significantly. It was not inclined to write that off without exhausting the alternatives. They experimented with throttle technique. They adjusted how crews managed steam pressure on approach to grades. They tried modifying operating procedures to get more reliable performance out of the third engine set, which sat beneath the tender at the rear and was the most difficult to manage. None of it resolved the core problem. The triplex was eventually rebuilt. The third engine set was removed. The locomotive became a conventional, if extremely large, articulated design. A machine that worked reliably in ordinary service, because it was no longer attempting something that ordinary service could not support. And quietly, without ceremony, the idea of the triplex as a solution to the helper problem was set aside. Not because it was badly made. Baldwin built it exactly as specified. Not because the engineering was careless. Meyer had thought through the mechanical logic with genuine care. But because the vision of the machine had outpaced the vision of the system it would operate within. The couplings, the boiler dynamics, the practical realities of mountain railroading. The triplex had been designed as if raw tractive force was the only variable that mattered. It was not. Here is what you have to sit with, though. The triplex did not fail because the concept of extreme power was wrong. It failed because extreme power, applied to a system not designed to receive it, destroys the system rather than serving it. The steel coupling does not care how impressive the number on the specification sheet is. It holds what it was rated to hold and no more. The boiler does not care how many engine sets are downstream of it. It produces steam at the rate physics permits. The mountain does not renegotiate its grade because the locomotive pulling against it is historically significant. These are lessons that look obvious from the outside. They are apparently very difficult to learn from the inside. When you are standing in front of something that looks like the answer to every problem you have been trying to solve. The railroad industry learned them, slowly, through the years that followed. The era of ever larger steam locomotives continued. The Union Pacific's Big Boy, the Chesapeake and Ohio's Allegheny, machines that surpassed the triplex in useful output by working with their operational environment rather than against it. They were powerful within the limits of what the system around them could sustain. That was the lesson. Not less ambition, bounded ambition. The triplex had pointed towards something real. The need for concentrated power on difficult grades was genuine. The desire to eliminate the cost and complexity of helper operations was rational. The direction was correct. The scale was simply calibrated against a world that did not exist yet. A world of stronger couplings, better boiler technology, more refined understanding of how steam behaved under continuous high-demand conditions. It arrived about 30 years too early and paid the price that pioneers usually pay. None of the three Erie Triplexes survive. They were rebuilt, then eventually retired, then scrapped in the way that most working machines are eventually scrapped. Without ceremony, without preservation, without anyone fully understanding at the time what they were losing. What remains is the record, the specification sheets, the photographs of something that looks, even now, almost implausible sitting on standard gauge track. A machine so long you cannot quite hold it in a single frame. So heavy the rail beneath it was measurably stressed by its presence. And the story that railroaders passed down to one another for decades afterward. About the locomotive that could snap a steel coupling without trying, that could split a freight train apart at the joints before the wheels had turned. That was not defeated by what it could not do, it was defeated by what it could. There is something in that worth carrying, because the triplex is not really a story about a locomotive. It is a story about what happens when you solve one problem so completely that you create a new one. When the answer you build is more powerful than the question it was designed to answer. That is not a failure of engineering. It is a failure of imagination. Specifically, the failure to imagine all the other things that would need to change alongside the thing you were changing. The triplex could pull. It could pull harder than anything that had come before it. It just could not pull the world with it. If you enjoy forgotten engineering experiments like this, subscribe. Every week we uncover the machine's history almost erased